In this video I show you how the Planck constant can be determined experimentally using LEDs. Planck's constant, denoted by H, is a fundamental physical constant of foundational importance in quantum mechanics. The constant was postulated by the German physicist Max Planck in 1900 as a proportionality constant needed to explain experimental black-body radiation. Planck later referred to the constant as a quantum of action. In order for the LED to light up, the electrons from the conduction band must recombine with the holes in the valence band. The energy delta E released in the process is emitted in the form of light. The size of the band gap and therefore the amount of energy released depends on the doping of the LED. Doping is achieved by introducing suitable materials. Of course, you can now measure the voltage individually for each LED at which it starts to light up, but I thought it would be more convenient to do this with a small customized PCB. The best way to explain this is by means of the circuit diagram. The LM1117 is a low dropout voltage regulator. The device is available in 5 fixed voltages. I use the 5 volts version. The input voltage at the barrel jack is therefore regulated down to a stable 5 volts. The two 10 microfarad tantalum capacitors improve the transient response and stability. The potentiometer RB1 acts as a voltage divider and is used to set the forward voltage. The rotary switch can be used to select one of the 5 LEDs. R1 is a series resistor for the LEDs. The ammeter is optional for measuring the forward voltage when current starts to flow. It can also be used to determine the voltage versus current characteristic of an LED. After the so-called Gerber files were sent to my PCB manufacturer, I received the PCBs a week later. I then fired up my soldering iron and populated the PCB. As usual, I finally cleaned the populated PCB with isopropanol to get rid of flux residues, which have a corrosive effect. Next, I mounted 4mm banana jacks on the PCB to be able to easily connect the PCB with multimeters. Almost all multimeters have 4mm banana jack connectors. To prevent the banana jacks from coming loose, a little Loctite is recommended, but only where no galvanic connection is required. Of course, the knobs for the rotary switch and the potentiometer couldn't be missing. To keep the PCB level, I used the mounting holes to screw in M3 brass standoffs. Since I didn't want to use an ammeter for the experiment, I also made a cable with 2 banana plugs for bridging. Such cables are extremely useful and easy to make yourself. You can buy the banana plugs in different colors as a set on Amazon or eBay. I always use 18AWG silicone-coated tin copper wire. Now it was time for a first functional test. For the experiment, a multimeter is now connected to the PCB and the DC voltage range is selected. The experiment itself is very simple. For each LED that corresponds to a certain wavelength, the voltage is measured when the LED barely lights up. The measured voltages are then noted on a prepared sheet. In total, I carried out the measurements on each LED 3 times. I then analyzed the data in Excel. The first step was to calculate the arithmetic mean of the measured voltages. Next, I converted the peak wavelengths taken from the LED datasheets into the frequencies. Since an electron volt is the amount of energy that a single electron gains or loses as it moves through an electrical potential difference of 1 volt, we can also express the measured forward voltages as energies in electron volts. If we now plot the data with a frequency on the x-axis and the energy on the y-axis and provide it with a regression line, we would expect this line to go through the origin, but this is not the case. Instead of E equals HF, we have E equals HF minus delta E, as it is the case with a photocell with a cathode material dependent work function. The question now is whether we can neglect delta E for the determination of the Planck constant, which corresponds to the slope of the regression line. To answer this question, we use the forward voltages from the datasheets and plot them for comparison. You can see that the two regression lines are parallel to each other, and it is actually only a parallel shift of the regression line on the y-axis, which is probably due to the fact that the light of the LEDs emits with a spectral width of 70 nanometers and more, and the LEDs already start to light up before the forward voltages specified in the datasheets. So we can finally conclude that the slope of the regression line is an experimental approximation of Planck's constant, which deviates only 5.3% from the exact value. Thanks for watching. Stay true, stay you.